All right, Assalamu alaikum. So we've seen the time dependent Schrodinger equation. We've seen the time independent Schrodinger equation as well. So let me just write down the equations again. So just before coming to class, I've also Shireen, क्या हो गया? Just before coming to class, I've updated the website with some reference material. The website was down for a couple of days. Sorry for that. Reading material for the past 4 or 5 lectures have been all pinpointed on the website. I've also uploaded a Python script, a notebook that you can access online. And you can put in your rotation operators and see the trajectories of the quantum state on the block sphere. It's a very easy to use Python script. Even if you don't know Python, I think just by the look and feel of it, you can wade your way through. So let me first of all kind of write down the Schrodinger equation. Yes, please. क्या चीज़? वो है, but it will be hard for you to find. So the time dependent Schrodinger equation, which is the real Schrodinger equation, which is all of it, is this thing. So this is our time dependent Schrodinger equation. And from this time dependent Schrodinger equation, we motivated a time independent form on the wave function. The wave function is the quantum state in position space. When you represent the quantum state in terms of position, you get a wave function. You can also represent it in terms of momentum, but we haven't touched that in this course. So the time independent form of the Schrodinger equation is minus h bar square over 2m, the double derivative of the wave function in space without the ket sign, plus the potential energy in space. How does the potential energy look like? Times the wave function into the total energy of the system. And so far we've solve this equation for a free particle. A free particle is a particle that has mass and moves in free space, which means in the absence of potential energy. And for a free particle, we've seen that the wave functions are something like E, A, E, I, K, X. This is the wave function representing a particle moving from left to right. And if you would like to also factor in the time dependence, we write this big psi. This big psi is the space dependent part alongside a time dependent part, omega. Okay, so this is what we've done so far. We also know that for a free particle, like an electron or a proton, something that has mass, we're not talking about a photon here, by the way, something that has mass, we also have the relationships P equals h bar k, which is the de Broglie relationship. You've learned this in your A levels. And we also know that the energy is h bar omega for such a particle. So this is all in front of us. But now let's try getting our hands on the time independent Schrodinger equation. We also know that if we do know the time independent part, we can get the time dependent part from the time independent part multiplied with this time variation factor. But this omega is E over h bar. Alright, so this is what we already know about the Schrodinger equation. Now the Schrodinger equation is important because it tells you how a quantum state changes with time. So it is the equation of motion for quantum systems. Newton's equations are the equation of motion for classical systems. Schrodinger equation tells us that how do quantum objects move in space and in time, provided we are at very small speeds, non-relativistic speeds, very small speeds. If you want to go to higher speeds, you need another equation. It's called the Dirac equation. So now let's look at some manifestations of the time-independent Schrodinger equation. The time-independent Schrodinger equation doesn't give you any time-dependent part, just a space-dependent part churns out of the time-independent Schrodinger equation. So let's look at one example, which is of an infinite well. Now, what is an infinite well? Suppose I have an electron, just one electron in an island of material, small piece of nanometer sized material, which is called a quantum dot, and I put that electron on that quantum dot, and the quantum dot is so small that it can only harbor a single electron. Just one electron can sit on that quantum dot, and this quantum dot, this thing here, just has one electron. It's a piece of semiconductor. It's surrounded by two metal pieces, two metal electrodes, and we give a negative charge to each metal electrode. So there are two electrodes. This is electrode 1, electrode 2, and this is our quantum dot. A quantum dot is just a small piece of a nanometer size material, semiconducting material, that can hold electrons. It's a reservoir of electrons, and we assume that there is only one electron on the quantum dot. Now the electron itself is negatively charged. So would it like to remain on the quantum dot, or can it hop onto the electrodes? Would it like to hop onto an electrode? No, because the electrodes are already negatively charged. So the electron, if it has been placed on the quantum dot and it's surrounded by those electrodes, it would like to remain there, and it would like to remain trapped on that quantum dot, because it sees very high energies, very high potential energies to its left and to its right. So this is an example of an electron being trapped along the x direction. Suppose this is my x direction. So the electron has been trapped in the x direction, and it's been trapped because of the presence of these very strong negative charges outside the quantum dot. Suppose the length of this quantum dot is L. Now if I would like to make an energy diagram for the electron from the electron's perspective, this is what the diagram is going to look like. So this is my x-axis, this is x equals L, this is x equals 0. So this is my x-axis, and my potential energy diagram looks like the following. The potential energy is extremely high at x equals 0, and it's extremely high at x equals L, so it goes to infinity at x equals 0 and x equals L, and in between the potential energy, suppose it's 0, and it's very high, infinitely high in this regime. So it's infinitely high, and it's infinitely high over here. So this is an example of an electron that is trapped inside a well. We call it an infinite well because of these impenetrable, very large potential energy barriers that surround the electron. Okay?
Sir, can you please repeat? It's infinitely high at x is equal to 0 and L, and beyond that?
It keeps its high at all points beyond this, and it's infinitely high at all points to the left of this, because the electrode is kind of extending to infinity on both sides. So the only possibility that that electron can live and reside is on a quantum dot. So it can only remain inside the length L. So now what we would like to do is we would like to solve the time independent Schrodinger equation for the electron for this simple scenario. This is, by the way, the simplest scenario that you can think of beyond a free particle. Now, how do we solve this time independent Schrodinger equation? The particle cannot be found here, and the particle cannot be found here. So if I break my system into three regions, 1, 2 and 3, then my quantum wave function in region 1, that is for x less than 0, my quantum wave function, let's call it psi 1x. What is this function going to be in this region? If I cannot find the electron here, what should the wave function be? 0. Alright. Likewise, for x greater than L, my wave function, let's call it psi 3. What should this be? 0. So I know that the wave function is 0 here and the wave function is 0 here. I want to find out what's the wave function of the electron inside the well, inside the infinite potential well. No. So we have to solve the Schrodinger equation for that purpose. That's what we would like to do. Therefore, and this is our Schrodinger equation. So outside the well, the wave function is 0. Physics tells us that the wave function is 0. So let's now solve the Schrodinger equation inside the well for that electron. So inside the well, what is the potential energy? What is the potential energy inside the well? 0. So let's write down the Schrodinger equation inside the well. So inside the well means x is greater than or equal to 0 and less than or equal to L. So in this region, in region number 2, our time independent Schrodinger equation is minus h bar square over 2m d square psi x dx square. The potential energy is 0. So the second term is 0 is equal to the energy of the electron. So the electron will have some total energy E. Alright. So this is E psi x. So we need to solve this equation. Solving this equation means we really want to find out what psi x looks like. So inside, so this is a small psi 2 here inside. So I just not going to write the 2 all over again. So this is my time independent Schrodinger equation. I want to solve this. So we've seen an example of how to solve a one first order differential equation. Now this is a second order differential equation because this has a double derivative. So we need to have some techniques of solving second order differential equations as well. I'm going to introduce one such technique today. Right? Have you ever solved the second order differential equation? Which course? Oh, okay. No, something here at SSC. Okay, no problem. It's easy. Life is easy. So, first of all, let me kind of reshuffle this equation a little bit. Minus h bar square over 2m minus E psi x equals 0. Correct? So I just do a kind of correct. Now this is my second order differential equation. Second order because it's the double derivative of the function. Now when I have a second order differential equation of this kind, one way of solving it is the following. Now this is a differential equation. I would like to write an equation auxiliary to this. Auxiliary means a satellite equation to this, another algebraic equation to this. So what I would like to do, first of all, in the first step, I would like to make the coefficient of the second order derivative 1, which means I divide both sides by this factor. So I get d square dx square psi x plus 2me over h bar square psi x equals 0. Now this is an electron. This coefficient here, I just want to replace it by something else. Can you guess by the look and feel of it what would be the dimensions of this coefficient? Remember, E is p square over 2m. Remember this formula over here? This is p square over 2m as well. So p square over 2m is E. So 2me over h bar square is p square over h bar square. So what I could do is, I just want to write another symbol for this. So my energy is p square over 2m. P is the momentum. 2m over E is P is h bar square k square. Correct? From the de Broglie relationship. Got it? So 2me over h bar square is k square. K is the wave number. So there is a wave associated with this particle inside the well. That wave is a quantum wave. It's also called a matter wave, and the time independent Schrödinger equation tells us what this wave looks like. And this 2me over h bar square has dimensions of the square of k, 1 over meter square. So what I could do, I could replace this with k square. So I could write d square dx square psi x plus k square psi x equals 0. Now this is my second order differential equation, the time independent Schrödinger equation for this particular problem inside the well. Yes, please, you had a question? All right, now how do I solve such an equation? In order to solve a second order differential equation whose coefficients are constant, there's constant over here. There's no x dependence on the coefficients, yes? K is the wave number, 2 pi over lambda. So there's a wave, k is the wave number of that wave. That wave is a quantum wave. It's called a wave function, yes?
So what is the name of k? K hai kya?
Wave number.
Wave.
All right, so when you have a second order differential equation of this kind, you would like to write an algebraic equation which is a cousin to this equation. That auxiliary equation, how do we write that? Look at the term which has the second order derivative and choose any symbol you like, q. Let me choose any symbol I like, q, and put a square on it, plus. Now this term doesn't have any derivative. It just is the wave function itself. So just look at its coefficient k square and I write down the coefficient k square and put this equal to 0. So this equation is an auxiliary or a supplementary equation to the differential equation. For example, if I have, let me give you an example. If I have something of this kind, say a naught d square psi dx square plus a1 d psi dx plus a2 equals 0. If I had this differential equation, the auxiliary algebraic equation that goes with this is a naught q square plus a1 q plus a2 0. Now this is a quadratic equation, an algebraic equation. I can solve this for q. Yes, please. It's some variable. Some variable, I give it a name q.
And how did we derive it in the auxiliary function? Q square plus k square.
So I'm now describing a technique to solve second order differential equations with constant coefficient. So I take the differential equation, and wherever a derivative occurs, I put a q in its place. In other words, just imagine this as a naught d square dx square plus a1 d dx sorry, there's a psi here as well. Sorry, I forgot this. There's a psi here as well. Plus a2, all of this acting on psi to give me 0. Right? So this differential equation is also this, written in a different form. I replace d by dx by q. I give this the name q. I replace this by q square. I get this. So this is just an auxiliary equation, an auxiliary algebraic equation to the differential equation. Now if I look at my Schrodinger equation, the auxiliary equation looks like this. I solve this equation. My variable is q. So what would the solution of this equation look like? What is q? Q is nothing. Q is just a variable here. What, when I solve this equation, what is the answer for this? What is q equal to? Q equals what? आप बताओ, आप मेरे को बता सकते हैं? आयोटा k स्क्वायर, स्क्वायर रूट भी तो लेना है. So this means this is q square equals minus k square. So take the square root of both sides. Q, the square root of k square is k. What's the square root of minus 1? Iota. But I can get a positive or a negative answer. Correct? So there are two possible solutions, plus ik and minus ik. I can check this. If I have plus ik as my solution, I square it, what do I get? Minus k square. If I have minus ik, I square it, what do I get? Once again, minus I square, which is I square minus k square. So in each of these cases, the squaring operation gives me minus k square. So there are two solutions to q, plus iota k and minus iota k. So I take the differential equation, I write the auxiliary equation and solve that auxiliary equation and find out the solutions of that auxiliary equation. Now once I've done that, I can predict what the solution of the original differential equation looks like. So the original if I knew the two solutions, so the two solutions are plus ik and minus ik. This tells me that my differential equation, whose solution is psi x, equals, what I do is I take the two roots of this equation and put them in exponents. So I take one root, plus ik, put it here, plus, then I take the other root, put it here. I put a plus sign in between and I put two coefficients a and b, arbitrary coefficients, because the second order differential equation I will have two unknowns in my answer. All right. So this will be a solution to the time independent Schrodinger equation for this electron that resides inside the infinite well. All right. Now what does this solution represent? What is, sorry, you want to put an x as well, x. So you put the solution and put the variable x as well. So this is the solution. What does the first term represent? What is EIKX? Remember your previous lecture, what is EIKX? What does it physically represent? Sorry? Physically, what does it look like? A wave. What kind of wave? A plane wave. It's a plane wave. And what does this represent, this term? Another plane wave. What's the difference between these plane waves? One, no, it's not up and down. One is moving to the left, the other is moving to the right. This is a traveling wave moving to the left. This is another traveling wave, but moving to the, this is moving to the right, this is moving to the left. So now inside the infinite well, I have two waves. One is moving to the right, the other is moving to the left. A free particle was only moving in one direction. This was a free particle over here. This thing, a free particle moving from left to right. Now we have a superposition of a left moving wave and a right moving wave inside the infinite well. Now when we have superposition of two waves, generally what do you get in normal physics? Two waves of opposite directions, same wavelength, same wave numbers, k is the same. You can get some kind of interference and a new kind of wave might form. What is that wave called? Stationary or a standing wave. So let's see what the wave function looks like inside the infinite well. So now you have two counter propagating traveling waves, one moving to the left, the other moving to the right. Let's kind of dissect this wave function a bit further and let's try to find out what these constants look like. What are these constants? So mathematics, so physics gave you the Schrodinger equation, you do a little bit of mathematics, you get a solution. Now comes physics again and you want to interpret this. So this is a cycle of arguments you would like to do in a normal physics course. So now we have a wave function. We also want to draw this wave function inside the infinite well. Now first of all, the wave function has some nice properties. The first property of a wave function is that psi is kind of finite. Psi cannot be infinite because the probability cannot be infinite. Second, in space psi needs to be continuous. Discontinuous wave functions do not make sense. For example, if I have x over here and somehow I plot the real part of the wave function by the way is complex, I cannot have a function of this kind in which there is a discontinuity at this x naught. This is non-physical because this leads to infinite energies. The change in wave function is abrupt here. It's infinite, changing in infinite manner that corresponds to infinite energies. That's not allowed. In other words, you can remember that the wave function needs to be continuous. The third property is that the derivative of the wave function, the first derivative of the wave function is also continuous. So there are three properties of the wave function, and they correspond to the finitude of energies. So we need to remember these properties of a wave function. They are a well-behaved wave function. It's called psi must be an analytic function. Well-defined first derivative, well-defined second derivative. Because if the first derivative is discontinuous, if the first derivative is discontinuous, this thing will become infinite. When this thing becomes infinite, the energy becomes infinite, and this is unphysical. So the wave function needs to be continuous, and the first derivative needs to be continuous. So now with these properties, we can unpack what these coefficients look like. And let's do that. So I draw my infinite well. This is my x equals L. This is my x equals 0. This is my x-axis. What is the wave function in this region? Here, what is the wave function? Bolo, bolo, don't be afraid. It's not negative, it's 0. The wave function is 0 here, because the particle cannot exist in this region. And what's the wave function beyond L? So the wave function is 0 at this point at x at the origin, and the wave function is 0 at L. At L. And beyond too, but it's 0 at L as well, right? Because of the infinite well. This well is infinite. Hypothetical, nevertheless, a good approximation. Now the wave function inside is this. So this wave function, so the wave function in, this is my x equals 0. This is my x-axis. What is the wave function in this region? Here, what is the wave function? Bolo, bolo, don't be afraid. It's not negative, it's 0. The wave function is 0 here, because the particle cannot exist in this region. And what's the wave function beyond L? So the wave function is 0 at this point at x at the origin, and the wave function is 0 at L. At L. And beyond too, but it's 0 at L as well, right? Because of the infinite well. This well is infinite. Hypothetical, nevertheless, a good approximation. Now the wave function inside is this. So this wave function, so the wave function in here is psi 1, here it's psi 2, psi 3, here it's psi 2, this thing. So here it's psi 2 is A E I K x plus B E minus I K x. So this wave function must match up with the wave function at this point. Correct? Because the wave function is continuous. So the value of this wave function and this wave function must synchronize, must latch up at x equals 0. Therefore, this function at x equals 0 must be 0. And at x equals 0, this is a plus b, because I put 0 here, this becomes 1, and so on. So at least I have some more information from the properties of the wave function. That information is that the a and b, which are the two unknown coefficients, they must add up to 0, which means that b must be equal to minus 1. So this means that this wave function psi 2x, I can simplify it a bit further. I can write this as a e I k x minus e minus ikx. Correct? This I can write as 2 iota a sine of kx. Correct? Yes, please.
So can we say that the derivative of psi 2 and psi 1 is same at x equal to 0?
That's also true. So this is our wave function. Got it? Inside the well. Now can I find this A? Is there another kind of condition, constraint that can help me find out A? What's that? So the sum of all the probabilities must be 1. So I'll do that later. But first of all, let me figure out another interesting property of quantum physics. It is as important a property as superposition, as entanglement, as interference, non-locality, and that property I'm going to describe now. Now if I look at this wave function here, I'm going to plot this later, but I also have to my disposal the property of continuity at x equals L. So I can get some further information from this condition. So at the other end point, I'm going really slow here. I'm trying to be very clear. So at x equals L, what's the wave function here at this point? 0. So this wave function must be 0 at this point as well. So at x equals L, my psi 2 at x equals L, this must be also be 0, but this is 2ia sine of kl. Alright. Now how is this equation satisfied? Can I have a equals to 0? That's one mathematically, yes, but then the wave function will not exist any whatsoever, which means there is no particle. But there is a particle. So a cannot be 0. So the only manner in which this can be satisfied is by putting this trigonometric function equal to 0. So sine of kl is 0. So when is the sine of a function, sine of some number 0? When kl is a multiple of pi. So this means kl must be a multiple of pi. Kl is a multiple of pi. N is some number. 1, 2, 3, 4, and so n is a natural number. So n is 1, 2, 3. N is any number. Okay, so this means k must only take up values n pi over L. K cannot be arbitrary. K can only take up some multiples of pi over L. So k, for example, can be pi over L. It can be 2 pi over L. It can be 3 pi over L, and so on. So now my wave function psi inside the well is, now what I could do is 2ia. Is all of this a constant? Yes. So let's call this C, right? Just want to simplify things a bit. A, by the way, is a complex number. 2ia can also be a complex number. So the wave function becomes sine of C of sine of n pi x over L, where n is a natural number. So this is my wave function. This is my solution to the Schrödinger equation. Now, is it possible to find out C. Is it possible to find out C, capital C, by some other constraint? No. Suppose, okay, one, I do know that if I take psi x and modulus square this, what does this represent? Probability density. So if I integrate this probability density over all of space, what should my answer be? 1. And this is true when n equals 1, when n is equal to 2, when n equals 3, and so on. It's always true. So let's find this thing out for n equals 1. So what I could now do, I could break up my integration from minus infinity to infinity in 3 regions. This region, second, third. In this region, the wave function is 0. Here the wave function is 0, so I'm only concerned with the integration in this region. These 2 regions give me 0, big zeros. So I'm only concerned with the integration over here, from x equals 0 to x equals L. So now if I were to do that, from 0 to L, bx. Now this thing, I take the square of this, C mod square. C is a complex number, x. What's the integral of a cosine of something? Sine. When I put the limits, this term just goes away, vanishes, because sine of 2 pi something is 0, sine of 0 is 0, so I don't care about this term. The integral of this term with these limits gives me 0. So I'm just left with C mod square L over 2. This equals 1. This means my C mod is 2 over L under root. And global phase doesn't matter. I can put any phase with C. So I just put C equals 2 over L. So my wave function, finally, the final solution for the wave function inside the well, in the well, in the infinite well. This thing is 2 over L sine of n, I bring back the n, pi x over L, where n is a natural number. Yes, please. Yeah, I just use this formula. I think sine square of theta is 1 minus cosine 2 theta over 2. Easy? समझ आ गया? So this is now the wave function for an electron or a proton or a neutron or any other quantum particle, massive quantum particle trapped inside an infinite well. Now we need to find out, what do these wave functions look like? And what are the further implications of this? What does this all mean? Why did I say that this is such an important result? First of all, let's see what these wave functions look like. Because you can't plot quantum states, but you can plot wave functions. Now, the wave function changes with n, with this number n. So I can put a small n here. The wave function depends upon n. N is not a variable, n is another number that's just popping out of this property of the wave function, that it has to be continuous. This n is an example of a quantum number. It's called a quantum number. N is a quantum number. This n is called a quantum number. You must have come across quantum numbers in your Chem 101 course, NL, ML, all of these come out due to similar kinds of arguments, similar reasoning. This is a quantum number. So the wave function depends upon n. Of course, it's a function of x, but this parameterization with n also takes place. So if you want me to plot the wave function, you need to tell me for what n. So let me plot the wave function for a few n's. So this is my well. Here's another diagram for another n, another diagram for another n, another diagram for another n. So let me first plot n equals 1, the wave function for n equals 1. This, by the way, is L, 0, 0, L, 0, L, 0, L. So if I were to plot this with n equals 1, what will the function look like? Sine pi x over L. What does it look like? A sine function. And 0 here, 0 outside. Continuity is preserved. Continuity of the first derivative will also be preserved. Or will it not? You'll have to check that. The continuity of the first derivative is not going to be preserved here because of this infinite walls, but that's a technicality. Anyway, this is the wave function for n equals 1. What does the wave function for n equals 2 look like? It's going to be this is n equals 2. Here there are nodes at the ends. These points are called nodes where the wave function is 0. Just start. I hope your mind is also rambling towards atomic orbitals. S, P, D, F. There are nodes over there too. N equals 2. 3 nodes. 2 at the ends, 1 in the middle. N equals 3 will have 4 nodes and 3 lobes. This is what it's going to look like. Just a nice sine function. The height of this is c. Alright? N equals 4 will have 4 lobes and 5 nodes. So let me try plotting this. Now let's kind of unravel the physics of this. First of all, different n's gives you different wave functions. Now the wave function can be real or complex. If I took a phase factor here, it could be complex, but that's beyond the point. But it's an oscillatory function and it's only stuck at the 2 points, at the 2 endpoints, because of the continuity of the wave function. Does this look like a standing wave? It looks, indeed it looks like a standing wave where the endpoints are the nodes. And is it symmetric with respect to the middle of this infinite well? It is symmetric because the potential energy is symmetric about this point to begin with. This potential energy diagram is mirror symmetric with respect to this mirror. Therefore, the wave functions need to be symmetric about the middle point. Right? They have to be symmetric about this point. And if I were, what does a standing wave in classical physics look like? What do you mean by standing wave? When is a standing wave formed?
When two waves traveling in opposite
Right, but there has to be a condition, yes.
Energy does not travel, only the particles.
Right, but okay. When will a standing wave be formed on a piece of wire? When the length is of a special kind. What is that length? The length must hold an integer number of half wavelengths. Only then can a standing wave be formed. The length should be an integral multiple of half the wavelength. So this has half the wavelength. This has 2 times half the wavelength, which is 1 wavelength, 3 times half the wavelength, 4 times half the wavelength. L is n times half the wavelength. But since k equals 2 pi over lambda, this would mean n over 2, lambda is 2 pi over k. This would mean n pi over k equals L. This means k equals n pi over L, which is the same condition as we've derived over here. So this length of the infinite well harbors an integer number of half wavelengths. That's the condition for a standing wave. So everything is making sense, all making sense. In fact, when Niels Bohr came before Schrödinger, and if you recall, Niels Bohr gave us the old quantum theory, and he proposed that if you have an orbit of an electron inside an atom around the hydrogen atom in nucleus, an orbit of radius r, then if we can associate a wave with an electron, then only such an angular momentum is possible in which this circumference holds an integer number of half wavelengths. It's exactly the same thing over here. So this circumference of an orbit of an electron inside an atom is 2 pi r. If this holds n over 2, lambda over 2 times n waves of the electron, the quantum waves of the electron, the matter waves, this is a kind of a quantization condition. So let's see if what does this lead to. This would mean 2 pi r. Now the Broglie relationship tells us that lambda equals h over p, correct? Or p is equal to h bar k. So n h over 2p and h. In fact, it shouldn't hold, since this is continuous, it should hold an integer number of wavelengths, because this is continuous. It can't hold a half, an integer of half, it must hold an integer number of full wavelengths because it's tied to it itself. So this is the condition. So if I write this as PR is NH over 2 pi, this is NH bar, this is PR. But what is PR? Angular momentum. So Bohr used similar ideas to tell us that the angular momentum of an electron inside an atom is quantized. But what is quantized here? Let's look at this word quantization. What is quantized here in this example? It must be the energy. So only precise patterns are admitted for the wave function. Each of these wave functions corresponds to one energy of the electron. Let's kind of bring that argument together. The energy, as we all know, what's the energy of our system? How do we define E? This is how we have, this is our relationship. 2me over h bar square has been put equal to k square. Let's look at it back again. Let's reverse this. We wound it, let's unwind it now. So this means that my E is h bar square k square over 2m. Now is k quantized? K is quantized, so energy must be quantized. So let's put this h bar square. What is my k square? K square is this thing, n pi over L. So this becomes n square pi square 2ml square. So the energy is also quantized. I can put a small n with the energy. So in infinite well, the energies of the electron or the proton, whatever the particle is quantized. Whenever we trap a particle, which means whenever we confine, I'll come to you, whenever we'll confine a particle to a particular region in space, its energy becomes quantized. A free particle is not confined in space. It can have any energy whatsoever. It can have any value of k whatsoever. But here only precise values of k are allowed. Only quantized values of k are allowed. Only quantized values of energy are allowed. So if I were to kind of write this down, this golden principle of quantum physics, this is what it would mean. Confinement leads to quantization. So if I were to draw this infinite well, for n equals 1, this energy is, let's call this part E1. So this is n square into E1. This thing is called E1. So if the electron is in the lowest energy state inside this well, it can have an energy equal to E1. This is its energy E1. That energy is h bar square pi square over 2ml square. This is called the ground state of the electron. Lowest energy state, the ground state. The next energy state is the first excited state. So that will be higher in energy. So this is my energy axis. I'm just drawing an energy level diagram. Now I don't have a qubit. A qubit has two energy levels. Here I have infinite number of energy levels for this electron, but they are quantized. So this energy here, what's this energy equal to? How much is this energy? What is this energy in terms of E1? 4E1 square. This is 4E1 square. 4E1. Then the next energy, 9E1. Next energy, 16E1, and so on. So the energy is quantized. If an electron were trapped inside this well, it can only have energy E1 or 4E1 or 9e1 or 16e1, 25e1, 36e1 and so on up to infinity. So this is the ground state. All of these are the excited states. It cannot have an energy in between. Right? So the energy is quantized. The wave number is quantized. The energy is quantized. The minimum energy, first of all, is the minimum energy zero? Can the minimum energy be zero? No. Even if you put this infinite well at 0 kelvins, lowest possible temperature, protected from the environment, still it will have some energy. So the minimum energy it can have is this E1. Sometimes this minimum energy is called the 0 point energy or the vacuum energy. Which means that if you have vacuum, a particle in its ground state, everything is in the ground state, lowest energy state, still it will have some energy. In quantum physics, there is no nothing. There is no nothing. Even vacuum has energy. There is no nothing. By the way, you cannot have zero energy. This is the minimum an object can have. Why? It's because of the uncertainty principle. How is this related to the uncertainty principle? Why? अच्छा सवाल है. Why? Why? Because of the uncertainty principle, I would say. You see, if let's look at the ground state. The ground state has this much energy, h bar square pi square over 2 ml square. The ground state has this wave function. Now, if I were to associate, if I were to ask you the question, where is the particle? What will your answer be? Somewhere inside that region, but you don't know where it is. It could be anywhere. If I were to take the modulus square of this wave function, I just square this. So this is modulus square of the yellow function. This is the probability density function. This probability density function tells me that the electron can be anywhere. If I do a measurement, it projects onto one point inside the well, but it really can be anywhere. So what's the uncertainty in the position of the electron? If I were to assign a value to the uncertainty, what would that be? What's an estimate for the uncertainty in the momentum? The realm of possibility of position. How big is that? L. किसने कहा? L. The uncertainty in the position could be of the order of L. So if that is the uncertainty in the position, so delta x is of the order of L. Okay. Now we know from the uncertainty principle, delta x, delta p has to be greater than or equal to h bar over 2. I know this. So it also means that, would this also be true? It would also be true. So I'm just doing rough calculations here. So if this much is my delta x, my delta p must be bigger roughly than h bar over delta x, which is L. Correct? Now this means if this is my uncertainty in the momentum, my momentum must be as big, must be at least this much if I were to make sense of momentum. The uncertainty in the momentum must be bigger than the uncertainty so that the momentum makes sense. So my P must be really larger than or equal to h bar over L. This is a kind of back of the envelope calculation. So my P must be this big. So if my P is this big, my energy is P square over 2m. So my energy should at least be equal to h bar square over 2m L square, which is roughly corresponding to this, of course with the pi square factor, because this is just an order of estimate calculation. So there is a bound on the energy. The minimum energy is bound from the lower end. There has to be a minimum energy. That minimum energy cannot be 0. That's the answer to your question, and a good question. Since there is uncertainty in the position, there is a minimum energy the particle must have. And by the way, if you squeeze the particle to smaller lengths, what is the minimum, the 0 point energy? How does that change? It goes up or down? Up. So squeeze the particle to smaller sizes, to smaller expanses, the uncertainty in momentum must go up, which means that the energy must go up. So squeezing to nanometer scale or angstrom scale or atomic scale causes large changes in the energy, large energies. All right, so this is 0 point energy. Any question about this? Yes, please.
Will we multiply the solution that we got for the wave function by e to the power minus omega t?
I'll do that. Now with this kind of reasoning, by the way, how do we interact with this well, with this electron inside the well? If you have an electron in the ground state here, you give it some energy, it will go to an excited state. But you need to give it the proper amount of energy. If you give it energy so that it's kind of, it might land here, it will never take up that energy. So how do you give energy to an electron? You might like to shine a photon on it, but that photon must have the right frequency, the right wavelength. So this electron can be excited to a higher level. Suppose an electron is here. If it's in this excited state, this is the first, second, third excited state with energy 16 E1. Then it might drop. Suppose it drops off to the next lower state. It makes this downward transition. It makes a transition. These are called transitions. When it does that, energy needs to be conserved. So this difference in energy comes out of this infinite well, perhaps through a photon, and that photon carries energy with it. That energy will be 16 E1 minus 9 E1, 7 E1. That will be the amount of energy carried by that photon. This energy is equal to h bar omega. Omega is the frequency of the photon, or hf. That determines the color of the photon that comes out, or the wavelength of the photon that comes out. So by looking at those photons, you can actually do spectroscopy of the infinite well. What are the energy levels there? So this is how spectroscopy works. This is how you can tell the spectrum from different stars, from different galaxies, from light bulbs, etc. So this is how energies are transitioning, and this is how energy is coming out in the form of photons. By the way, I've written the wave functions. Can I write the quantum states as well in ket form? Now, how do I write a ket? I just put a label inside the ket. Ket 0, ket 1. Now the thing is that I don't have a qubit, I don't have 2 levels, I have many levels, infinite level systems. So this energy corresponds to a ket. It corresponds to a wave function. A wave function is also a ket in space. So this energy level, I can call it, let me redraw this. So this is getting a bit cramped. So on. I can call this state ket E1, correct? Because the electron has energy E1 here. I can call this state ket E2. Ket E3. Likewise, ket En. Right? So these are kets. And if I want to write the function for this energy level, this ket, that will be psi of n, which is now a function of x. Is this quantum state En projected onto space, and that will be 2 over L sine of my n is n by x over L. Correct? So these are just kets over here. These are the corresponding wave functions. So suppose suppose I just take some value of n. Let me focus on ket E3. Now this is a very important point. I think, let me draw the wave function here. This is my wave function, psi 3. N is now 3. By the way, I can also label these kets as simply ket n, because n just labels everything. N just tells me everything about the state. It tells me the energy. It tells me the wave function. N is everything. N is the quantum number. N में पूरा जहां आबाद है. N सब कुछ है. हाँ, क्या सवाल है आपका? ऊंची बोलो. नहीं. Any quantum state can be written as a ket, not necessarily qubits. Now this is our wave function. Let me focus on this wave function. X, this is L, this is 0, 0 elsewhere. Now this is a wave function. Question, first question, where is the electron? Anywhere. So this is not a legitimate question to ask. At best, we can only assign a probability density function. If we were to do a measurement, this is the probability the electron might be found here. So if I take this wave function sine 3 pi x over L and I modulus square it, I get this. Now is psi 3 x mod square. This is a probability density function. Now I might ask you, what's the probability of locating this particle in the first 1/3 of this well? I integrate from this point to this point. By the way, this is an equal distribution, so this will be 1 over 3. 33% probability is if you were to do a measurement, the electron will be located in the first 1/3, 3 possibility in the second, and so on. Question is, Now, when you study chemistry, for example, you draw a p orbital. This is a p orbital. It's one of the p orbitals. What does this show you? What does this represent? It's actually a wave function, and some genius guy has tried to draw a 3-dimensional wave function on 2 dimensions. So this is a 3-dimensional wave function. It's a cutout of a 3-dimensional wave functions. And this, if it's the wave function, this might have a positive part and a negative part, just like a positive part and a negative part. This point is called a node. Likewise, these points are called nodes. So the question is, what's the probability of finding, locating the particle right at the node? 0. So this is kind of paradoxical, because there's some finite probability of locating the particle here and here. But how does it move across the nodes? If it moves across the nodes, there must be some finite probability of locating the particle here. But that's not how we look at electrons. That's not how we look at quantum systems. This is a wave function, a total picture of this wave function at one point in time. Right? So there is 0 probability of locating it at the node, but that doesn't mean that the electron cannot pass through. The electron is everywhere, even though it's a part. So when you detect an electron, it acts like a particle because all of its energy is coalesced into the detector. But before that, it's like a wave spread out. Now, how does this change with time? If I were, this is my wave function, the white is my wave function. This is only the space part. This must also change with time. How does it change with time? So if I were to look at the change in time, just one last bit. Psi x of at t is this wave function 2 over L sine of 3 pi x over L. Now comes your question about the time dependence. E minus I, the energy of this system, which is E3, which is 9 E1 T over H bar. All right. Now all of this is some frequency. 9 E1 over H bar is some frequency. Some frequency. So let's call this term E minus I some frequency. Let's call it omega 3 because it's the third level, n equals 3. Now I need to multiply this thing with this time dependent factor. And this, by the way, renders this wave function complex. It becomes complex because it's a complex number. But if I were just to plot the real part, I take cosine omega 3t. Now the wave function is a complex number, so if I were to draw just the real part, this part has to be multiplied by cosine of omega 3 into t. What happens is that at some point this function is like this, at some other point the function becomes this, then at some later time it becomes this. sorry. So it oscillates. So it's a standing. That's what a standing wave is. So this is three levels, and it's oscillating. The nodes always remain the nodes. That's what a standing wave is. But it's oscillating with the frequency depending upon the energy. Higher the excited state, higher will be this oscillation. Right? So this is really what an infinite well really means. In the next lecture, we'll just spend half the lecture on quantum mechanical tunneling, some strange potential landscapes, and then we'll move on to other exciting stuff next week. Thank you.